Annenberg Media.
This is probably a familiar scene, one that's becoming commonplace nationwide. Concern about the environmental impact of dumping or burning trash has motivated many communities to begin recycling programs. Separating reusable materials from plain old garbage can actually bring down the overall cost of trash disposal. So recycling makes good environmental sense and good financial sense as well. This recycling collection center has a basic operating rule. Residents must separate materials into specific groups: plastic, glass, metal, paper. The cost to the town of hiring workers to do that job would be too high. Cities and taxpayers see recycling as a good idea when it doesn't cost more than other disposal alternatives. When everyone follows the rule, there's a real benefit: money. Money that comes from selling the reusable materials. So far, so good. But where's the algebra? Well, recognizing particular things for what they are, identifying similarities where they exist, and manipulating that information to get useful results, these are skills all basic to algebraic reasoning, the language of mathematical problem solving. In this program, we'll learn some commonly used terminology, allowing us to begin speaking this new language called algebra. We'll learn to recognize different sets of numbers and how to avoid common mistakes in their use. We'll begin to unravel or simplify mathematical expressions by collecting like terms. And so we can have some fun using this stuff, we're going to set up some algebraic expressions and simple equations by examining a few everyday situations. Think of algebra as a language, which, like any language, is used to communicate ideas. Now, every language builds on an alphabet, a group of letters. We agree to use this particular collection of letters, written words, to represent specific concepts. From these words, we build sentences according to certain rules. Well, if algebra is a language for mathematics, then it also has to be built from an alphabet, and it is. We'll begin to understand the language of algebra by examining the role of numbers as an essential part of that alphabet. But numbers are not all alike in terms of the rules of algebra. There are actually several different alphabets, different groups of numbers called sets. So our first step is to identify some of the fundamental sets of numbers. It's time for a concrete example. Unfortunately, they don't recycle concrete here. But we can get a solid start with this line of thought. For us, this is a simple blank stripe of no particular importance, but it represents the cornerstone of modern mathematics and gives us a way to begin talking about sets of numbers. It's called the number line, and the marks that brought it into existence forever separated our Stone Age ancestors from all other animals. People began to keep records of individual events in their lives, say the number of hunts or harvests, tribal deaths, and lunar cycles, for example. By making it possible to predict seasonal change and tribal needs, these records improved a particular group's chances of survival. With this record keeping, counting was born. Such tallies, though sometimes kept as chisel marks on a stone or slashes on a cave wall, most often were kept on a piece of bone. Here, for example, is a piece of antler found in France and dates from around 30,000 BC. This simple method of keeping records had drawbacks. Among others, if the bone was misplaced or the cave wall damaged, the information was lost. With the expansion of trade, more adaptable counting systems became essential. It was impractical to count identical marks every time you needed to check the inventory. Unique individual symbols made it possible to tell where a person was on the number line without having to see and count the whole line. So it's counting that gave us our first number line. And units on this line are called, appropriately enough, natural numbers. The dots, they indicate that the numbers continue on endlessly. Let's go to an everyday source for a few examples of natural numbers. And what could be more everyday than the newspaper? Hey, what's this? Well, we know what this is. It's something the Arabs invented centuries ago, zero. You know, zero's hard to talk about. It's a symbol for nothing. But nothing is actually a pretty important something in mathematics. With the inclusion of zero, we have a new set of numbers with a new name, the set of whole numbers. Now, suppose we extend the number line to the left, beyond zero. We can think of the numbers on this portion of the line as being the exact opposite of the counting units on the other side of zero. We know them as negative numbers. With the inclusion of negative numbers, our number line now represents the set of integers, positive integers to the right of zero, negative integers to the left. With just a little twist, we recognize a portion of the set of integers as a thermometer. Often you hear degrees below zero called minus so-and-so degrees. Now, technically this is incorrect. Minus applies exclusively to the process of subtraction. To confuse negative with minus may seem trivial, but in the precise language of algebra, confusion can be devastating, or at least lead to the wrong answer. Now let's go to another part of the paper to find still other types of numbers. Here. If you've ever followed a cooking recipe, you've worked with portions of whole units or fractions. Half a cup of flour, or a third of a cup of oil, whatever. Fractions represent proportions or ratios between things. All the numbers that we've looked at so far can be written in fractional form as the quotient of two integers. Any whole number, for example, can be written as that number over 1. All fractions belong to another set of numbers, rational numbers. When we divide the numerator of a fraction by its denominator, say for example with the fraction a half, we convert that rational number into a decimal. Now here, 1/2 is equal to 1 divided by 2, which is equal to 0.5. So the decimal equivalents to fractions are another way of describing rational numbers. Now, all of these decimal numbers are rational numbers. The decimal equivalent to 1/3, that's 0.333 ... is rational because there's a consistent pattern to the way in which the numbers repeat. Now, here we have the decimal equivalent to 1/7. Now, it too is rational because the pattern of numbers repeats endlessly. By now you might be thinking, if there are rational numbers, maybe there are irrational numbers. Well, there are. Now, here's one that you've probably seen before. This symbol, the Greek letter pi, represents the number used in calculations to find the circumference and the area of a circle. Now, I use this symbol because I can't accurately show you the number it represents. Here's an approximation of its value. There's mathematical proof that the numbers go on endlessly and do so with no repeating pattern. This characteristic, which is true of all irrational numbers, puts them in a distinctly separate set. But these sets of numbers, rational and irrational, together make up the set of real numbers. Separating numbers into sets is essential in algebra because not all mathematical rules apply to all types of numbers. By referring to specific sets of numbers, we can clearly make appropriate distinctions. In comparison to our everyday use of language, algebra is a very precise method for communicating ideas. Now, I can safely say that this is a can, but then again, so are these. The meaning of the word can is broad and rather imprecise, but mathematics is precise. Now, no matter what else this can may be, it's still one can. This is one can, and this is one can. Now, all these cans add up, and today they add up to quite a problem. It's increasingly important these days to understand the economics of recycling. I've decided to begin by finding out the dollar value of recovered material. So that I can make comparisons between recycling centers, I'll take figures from 3 different cities, 2 about the same size and 1 much larger. Since scrap is sold by the ton, that's the appropriate unit to talk about. I also know that material is picked up and taken to processing plants every month. In order to keep the information organized, I'll set up a chart. I have data from 3 different cities, so I'll make room for 3 columns and put a city at the top of each. I'll then label rows with each different type of material. This row is for glass, so under Ashfield, I'll put 2, indicating the number of tons of glass collected during the sample month. Now again under Ashfield, I'll enter the figures showing the tons of metal, 3, and the tons of paper, 4. Now I'll take the rest of my data and fill out the chart. I don't know the dollar value for each of these materials, but I can use the symbol X for the dollar value per ton of glass, Y for the value per ton of metal, and Z for the value of 1 ton of paper. You didn't really think we were going to get too far into this without seeing variables now, did you? The 9 quantities represent the product of a number and a variable. They are each called terms. 2x is a term. It is the product of the number 2 and the variable x. The term is itself made up of 2 factors, 2 and the variable x. 2x stands for the dollar value of glass collected in 1 month in Ashfield. To find out the total value for all the materials from all 3 cities during the sample month, I'll add all the terms together. A collection of terms like this is called an algebraic expression. Now, if I spell out the value I'm seeking, I can introduce another symbol in the language of algebra, the equal sign, which you might think of as a mathematical verb. This algebraic expression is now called an equation. The expressions on both sides of the equal sign have the same value. Let's see if we can make this a little less awkward. Looking at the first 3 terms, we see that each has only 1 variable, x. X is called a common factor to each of the 3 terms. And since it's the only variable in each term, we can refer to them as like terms. The presence of a common factor allows us to simplify the expression 2x plus 3x plus 15x. We take the 3 factors associated with x, 2, 3, and 15, group them together inside a set of parentheses, and multiply the entire quantity by x. The common factor x allowed me to use an algebraic principle called the distributive property. I'll use this property again to simplify the group of like terms with a single y factor and the 3 like terms with a common factor z. Using basic math skills, we can simplify this expression to 20x plus 27y plus 49z. This is a much more concise way of stating our original expression. Later in this program, I'll introduce you more formally to the distributive property and several related rules used to simplify algebraic expressions. With a little research, I found current-day values for the variables x, y, and z. Substituting those values into my equation and doing the appropriate arithmetic, I arrived at the current gross dollar value of the materials recycled during the sample month in these 3 cities. As you might well imagine, the price per ton of these materials fluctuates, and so do the number of tons collected. The equation provides a clear and concise framework into which changing values can be easily inserted. Studies like this could be used to estimate potential national revenues or to set up models to evaluate the efficiency of programs in various cities. While doing research for my recycling study, I sorted through a lot of information. Here's a small rational number of it. Get it? Fraction, rational number? All right. Now, if I were to ask you which set of numbers is represented by these particular numbers, what would you say? Well, whole numbers would be right. We see 0. But the set of integers and rational numbers would also be right since they don't exclude 0. These numbers are, of course, also real numbers. Here's some other numbers from the set of real numbers, and these have quite a following.
Little high fly ball into shallow center field. Roberto Kelly setting himself. Jody Reed heading for the plate. Here comes the throw. And not in time. He scores. 3-1 Boston.
The game of baseball is as thick with numbers as it is with heartbreaks. From the 162 games that make up a team's normal season to the multitude of statistics that spill out onto the sports pages after every game. But be careful. Things are not always what they seem. For instance, does the batter who is walked but left on base at the end of the inning show up in the at-bats column? Well, let's talk with one particularly qualified baseball fan.
Hi, don't let the jacket and hat fool you. I'm Herb Gross. I've been a professor of mathematics for 37 years, but I've been a baseball fan for 55. And I guess what that tells you is I was going to ball games and looking at batting averages long before I understood fractions, decimals, or percents. Have you ever looked at a box score and tried to decide from looking at the box score how many men batted? You can't simply add up the at-bats, because if a player walks, he's still a batter, but he doesn't show up as an at-bat. The mathematical analysis says, look, there are only two possibilities. For every player who bats, he either made an out or he didn't make an out. If he didn't make an out, he either was left on base or he must have scored. Those are the only three possibilities. Therefore, we can now write down a mathematical formula that will tell you the number of people who batted in the game. Namely, if we let B stand for the total number of batters, and if we let O stand for the total number of outs, L for the total number of men left on base, and R for the total number of runs scored, the formula becomes B equals O plus L plus R. In other words, this says in the language of algebra that the total number of batters is equal to the number of men who were out plus the number of men who were left on base plus the number of men who scored. One of the things a lot of fans are interested in is something called the magic number. In other words, when can the fan heave a sigh of relief and say, if the worst possible thing happens and my team loses all of the rest of their games and their guys win all the rest of their games, we're still safe? How can we tell when that's going to happen? Let's see how we can figure out the magic number now just by looking at the standings. I look to see how many games my team won. I don't care about what they lost. I look to see what the other team lost. I don't care what they won. I take my victories added to their losses. 80 plus 70 is 150. The magic number at the beginning of the season was 163. I now subtract the 150 from the 163, and I wind up with 13. 13 is now the new magic number. So here's a case where you can look right at the newspaper and mentally add up wins, losses, subtract from 163. Now, if we wanted to write this in the language of an algebraic formula, was at the beginning of the season, but how do we figure out what the new one is? We said we took our victories, added to the other team's losses, and subtracted that from the original magic number. So now the magic number in algebraic form looks like M equals N plus 1 minus the quantity W plus L.
Setting up an equation to determine how many people batted or the magic number for my team can be fun. In fact, some people make for keeping a clear connection between an algebraic expression and the situation it describes. We could choose any variables to stand for the baseball words, say M through W from the alphabet, but the resulting expression would be a little confusing when trying to remember what each variable stands for. It would be wiser to provide a memory aid by letting the baseball words suggest the name for the variable. So, avoiding duplication, I'll do just that to get this expression. Notice that I used U to stand for the outs variable instead of O. Why? Because in the haste of calculations, there could easily be confusion between the letter O and the number 0. Being a baseball kind of guy, I often eat baseball kinds of food. Here's a view of one of my recent purchases at the local grocery store. I can't remember the exact number of each item I bought, but I can remember the price. So using memory aids and choosing the variables we could label the hot dogs D, the buns B, the chips C, the relish R, and the soda S, and set up this expression. But choosing variables this way sometimes has problems. The expression as shown cannot be simplified because the terms are unlike terms. But I know I bought as many packages of buns as I did packages of hot dogs, so I can change the variables associated with each to a single new variable. I'll use X for the number of packages of each. Likewise, I bought the same number of bags of chips as I did bottles of soda, so I'll assign a new variable, say Y, to both of those items. Now, with the common factor X present in the first two terms, I can simplify this part of the expression using the distributive property, which we first used in our earlier recycling equation. In order to apply the distributive property to the two Y terms, it'll be easier if we first move them together, so I'll rearrange the expression accordingly and then simplify to get this expression. The distributive property is, of course, not the only rule in algebra. There are many more. There is, in fact, a rule governing the way I can reorder an expression, as I just did when I moved the two Y terms together. Now, collections of rules are used to define particular systems. If you were to ask me to define the game of baseball, I would probably end up telling you the various rules that govern the game. Algebra has similar defining rules, or as they're generally called, axioms. There's a collection of axioms that defines the use of real numbers in algebra. The distributive property can be stated in the form of one of these axioms. In order to state the axiom for the distributive property as clearly and broadly as possible, we'll use the variables a, b, and c to stand for any numbers from the set of all real numbers. Next, I'll write a times the quantity b plus c equals a times b plus a times c. This axiom is true for any real numbers. Let's try a few. We'll let a equal 3, b equal 8, and c equal 4. Now, 3 times the quantity 8 plus 4 is equal to 3 times 12, which equals 36. And 3 times 8 plus 3 times 4 equals 24 plus 12, which also equals 36. Now, this axiom can also be turned around to read a times b plus a times c equals a times the quantity b plus c. Looking at both ways of stating the distributive property, we notice that this property has the ability to turn products into sums and sums into products. I used the distributive property in the grocery store expression to change the sum of the two terms, x times $1.79 and x times 89 cents, into the product of two factors, x and the quantity $1.79 plus 89 cents. In its application to both addition and multiplication, the distributive property is unique. The other axioms that we'll examine have two forms, one form for addition and a different form for multiplication. This next axiom, a plus b equals b plus a, is the commutative property for addition. This is the property that allowed me to reorder the terms in my grocery expression. Using this property, I can actually add numbers in any order without changing the value of the expression. While this rule may seem obvious, be careful not to assume that there's a corresponding rule for subtraction. There isn't. Clearly, 5 minus 3 doesn't equal 3 minus 5. Now, the axiom stating the commutative property for multiplication is a times b equals b times a. The commutative property for multiplication allows us to multiply numbers in any order. As in the rule for addition, this rule hardly needs to be checked. We can easily see that 4 times 5 equals 5 times 4. Now, if you're expecting to see a commutative property for division, you'll have a long wait. It doesn't exist. 15 divided by 3 does not equal 3 divided by 15. These next axioms illustrate the associative property for addition and multiplication. In both, the order of the variables doesn't change. What does change is the grouping or association of numbers as defined by the parentheses. All these particular rules say is 5 plus 3 plus 7 equals 5 plus 3 plus 7 for addition, and 5 times 3 times 7 equals 5 times 3 times 7 for multiplication. Now, let's take a quick review of some of the ideas that we've covered. This expression is called an algebraic expression. This is called a term. These are all variables. You could also call them factors. I'm reordering this expression using the commutative property for addition. What type of factors are these? Common factors. I'm changing this expression using the distributive property. And if you'd like to review the different sets of numbers, just pick up any section of the newspaper and test yourself. Oh, and watch out for this type of mistake.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.